Hi everybody. In this Hi everybody. This video builds on lecture 1 for molecules. So in this lecture we're going to talk more about the covalent bond. Last time we really talked about a form of covalent bonding called ionic bonding, but we want to talk more generally about the covalent bond this time. So we're going to talk about that, talk about bonding, anti-bonding, wave functions, talk about what an energy correlation diagram is. On this slide I have a picture of Gilbert Lewis. And Gilbert Lewis was a pretty famous chemist. He was at Berkeley. If you've taken chemistry, you've learned about the Lewis dot structures. So he is considered to be the discoverer of the covalent bond. A couple interesting facts about Dr. Lewis is that he was nominated 46 times for the Nobel Prize in chemistry, but he never won it. He also coined the term that you're all familiar with for a quantum of radiant energy, the photon. So he actually coined that term. Okay, so let's talk about the covalent bond. Okay, so when we're considering covalent bonding, we have to consider that the electrons that are involved in the bonds are not orientated with respect to just one nucleus. They're not near one nucleus or the other. They're actually shared. So we'll have to deal with the motion of electrons in the vicinity of more than one nucleus. We also have several electrons. We also have several electrons that affect the motion and the energy. Okay. So to start with, we're going to take the simplest covalent bonded molecule that we can have, and that's just simply an H2+. So let's start with that. So we have our two hydrogen nuclei, just two protons. And I'm going to say maybe the origin is at the one on the right here. I'm going to put a vector, displacement vector, I'll call R, big R, that goes to the other nucleus. And then we have our electron up here somewhere. And let's say from the origin up to that electron, let's call that little r vector. And then from the other nucleus to that electron, let's call that little r prime. So we have big R plus little r prime has to equal little r. Let me write it like this. Little r prime is little r minus big R. Okay. Now, what are we interested in? One of the things we're interested in is the energy. So let's write the potential energy down. And I'm going to write it as a function of little r. Now let's assume big R, the displacement vector between the two protons, is some constant right now. So with respect to the first proton, number 1 here, you get ke squared, negative ke squared over little r. And then we have a potential energy due to the other one, too. So plus negative k, the other proton, negative ke squared, and that distance is r prime, but we could write that as r minus big R, little r minus big R. So there's our potential energy. By the way, for H2 plus, big R is approximately, at least at equilibrium, 0.1 nanometer, just to give you a sense. So if you looked at a cross section, you remember this potential energy is three-dimensional. But if I looked at a cross section of it, let's let this be the zero energy line there. And let's say I have one of the nuclei here. So maybe this is just some distance, r. It might look something like this. So what'll happen is, if this doesn't really mean anything other than to locate where the center of the two hydrogen atoms are. This is the energy here. The electron might have some energy here, and it might tend to bounce around between these turning points here around this proton, but then it can tunnel through, and then it might bounce around here for a while, and then tunnel through and bounce around here for a while. So that's the general idea. And the tunneling time for protons for H2 plus is on the order of a second. So about every second the electron will go from one side to the other. It's much slower as the protons get farther apart. Now let's talk briefly about the wave function for this electron that we have that's involved in the covalent bonding here. So one way to treat this, and the way we usually treat this, is it's a time-independent mixture of atomic-like wave functions. So we'll say the wave function for the electron, I'll put a little e up there, is a wave function relative to the number 1 proton, number 1 hydrogen nucleus, and then we can put plus, or we can put minus the wave function relative to the other nucleus. Now, the subscript A is a label that stands for the quantum numbers. So it stands for the quantum state. You know the quantum numbers N, L, M. Neglect spin for a minute. So we have this quantum state plus or minus this wave function. Let's pictorially just try to represent that. So here is some represent distance this way. This is our wave function amplitude vertically. Here is 0, and let's say here is big R. So that's where our nuclei would be located. So let's say we have a wave function psi A around the first nucleus plus psi A around the other. How might that look like? Maybe it looks something like this. If you add these two wave functions together. So I got this first one, it goes like this, and then maybe the second one, and overall they look like this. So let's call this the symmetric wave function. If we choose the other, so here's this the wave function this way. If If I choose the minus, what might these look like? It's the wave function. So if we take the first one, centered around R0, and then the second one, here's R, here's 0. And what would we get? The overall wave function might look something like this. So we'll call this the anti-symmetric case. Now, you know what is one of the things that are important about the wave function is the square of the wave function, because that tells us the probability density. So if you look at the symmetric case, and here's the square of the wave function, what might that look like? You might expect it to look something like this. Get the idea? And if we look at the anti-symmetric squared, so this is the symmetric squared, the anti-symmetric squared, what would that look like? Well, oops, it look maybe this similar, but the difference is that at some point it will go to 0, where the symmetric case will not go to 0. So that's an important point. So these probability densities lead to different energies for the electron. Now, to try to explain that, I'll go back to one of the things we know. That's the particle in the box problem. Now, of course, we're talking about different beasts here, but I think you can get the idea if we go back and remember the particle in the box problem. So for the particle in the box, we had the energy is equal to some constant, I'll call E naught n squared, right? One-dimensional case, particle in the box. Oops. With infinite sides. So think about, obviously, if you have n equals 1, you have E1 is E naught, and if you have n equals 2, you have 4E naught. Different energies. Remember what the wave functions look like for this one-dimensional particle in the box with infinite sides. For the n equals 1 case, the wave function looks something like that. And the probability density then looks something like this. And for the n equals 2 case, what did we have? Wave function looks something like this. And the probability density look like this. So what I'm trying to convince you of by this is say that the symmetric case is a lower energy than the anti-symmetric case. So it's true for the particle in the one-dimensional box, and really without proof, just trying to make a comparison. I'm trying to convince you that it's true for this too. So this will lead, symmetric case will lead to a lower energy than the anti-symmetric case. So we're going to say, we're going to call the symmetric total wave function, we're going to call that the bonding wave function. Bonding. And the anti-symmetric is going to be the anti-bonding. Why? Because which case do you think the electron wants, wants to have. It wants to be in the lower energy state. So it's going to want to be in the symmetric total wave function. So the symmetric case leads to lower energy. We call that the bonding wave function, or the bonding orbital. We call these orbitals for the electron, and this is the anti-bonding orbital. Okay. So obviously the energy of the electron is going to depend on things like the distance between the two nuclei and the distance from the electron to the nuclei. So let's look at how the energy of the electron is correlated to the distance between the two nuclei, the two hydrogen nuclei. So now we're thinking about the energy of the electron. And R is the distance between those two nuclei, if you remember. Big R. So what happens when R is 0? The two nuclei are together. Well, what do you have then? You have a nucleus that has a plus 2 charge, and you have the electron orbiting that. So that's just a hydrogen-like ion, okay? And we know what the energy should be. It's this. So when n equals 1, when R is 0, we'll call it E1. Z is 2 in this case, you'll get negative 54.4 eV. And when n is 2, you'll get E2 at a higher energy, negative 13.6 eV. Negative 13.6 is higher, closer to 0 than negative 54. So that's when R is 0. So let's make a little energy diagram here. This is energy in EV. And let's say the bottom here, this is negative 54 EV. And across horizontally, that's going to be the distance between the nuclei, big R. So we have at least two possibilities. When n is 1, the energy could be 54.4 eV, or if n was 2, we could get negative 13.6 up here. So what I'm going to suggest to you is that this is down here, the lower energy is the symmetric case. And for the higher energy, that's the anti-bonding orbital. That's when R is 0. So what happens? Well, we can take the other limit when R approaches infinity. And we're going to assume at that point that the electron stays around one of them. That the electron goes with one of them. What is the energy of the electron? Well, then it's just a hydrogen atom, right? And in the ground state, then it's, so when we go way out here, it's so no matter where it started at, we know eventually that when they get separated far enough, it has to go to the 13. That should be at the same level as that. Up to the 13.6 eV. We don't necessarily know what's in between, but I'll show you how we determine in that. We can estimate what the energy of the electron is as a function of R by looking at the energy eigen equation, or the Schrodinger equation. So we can put in, let's say, the symmetric wave function, and we can change big R, and we can find out what the energy is as you move along here. This is called a correlation diagram. Okay, that's it for this video. The next lecture, we're going to start talking about the spectrum you would see. And again, we'll use a diatomic molecule as our example. So I'll see you next